Yeah.
the completion part. So that part you can record with Noman, I think.
Okay,
And,
fantastic.
For
I'll
those
just stay in the meeting.
Yeah, you please continue. For this, if you would like to, this is the lunch time.
Okay. Okay, great. So yes, I want to discuss an example that outlines Kapranov's theorem. So let me mention Kapranov's theorem again. And Kapranov's theorem says if we take a polynomial over the previous series in two variables, because we're discussing about plane curves right now, then the tropicalization, meaning taking minus y component y's of the curve defined by this polynomial. Then we have to take a Euclidean closure because there's only going to be a point set in Q to the 2, and we want to have sort of the dense image in R to the 2. Then this is the same as the tropical curve defined by the tropicalization of this polynomial P. And this theorem is a bit of a miracle because on the right, we have this degeneration of an algebraic curve, which is a very, very strong degeneration because we're forgetting so much and only keeping minus valuation of the points. And on the other side, we have a piecewise linear weighted graph in R2, satisfying balancing. So this is where the combinatorics are. So what we are saying is that our degenerations of algebraic curves are combinatorial objects. And this is the motivation, this is what is behind the tropical idea. And now we had an example where we wanted to show that, to show how Kapranov's theorem works. And for this example, we picked just a linear polynomial to make an easy example. So x plus y plus t in the field of previous series, adjoint xy. So all my previous series coefficients right now are very easy previous series. They just have one term, but that's okay. The finite series are also series. So v of p is then a line and can be parameterized. And this parameterization makes it easy to understand the tropicalization, which in general is not so easy. So we can parameterize this. We can write this line as the set of points of the form S minus T, where S is a previous series. And now we can use this to understand the tropicalization of those points, minus val component wise of those points. That's what we want to understand. So we have case 1. What if the valuation of S is bigger 1? Then, as we add the minus t in the second component to our minus S, the smallest exponent will now be the 1, which is in this minus t to the 1, right? So then the valuation of minus S minus t is going to be 1. And now we have to think of the minus signs. We have to take the minus signs into account because we're mapping a point S minus t to minus val S minus S minus t. So minus val of the second component is going to be minus 1. And minus val of the first is smaller. So we obtain a ray pointing from minus 1 to the left. Then we have case 2. What if the valuation of S is less than 1? Yeah, so it starts with like t to the 1/2 or t to the minus 2 or something. And then if we add the minus t will just be a term of higher order. It won't even do anything to the term that has the smallest exponent, so the valuation of minus s minus t is going to be equal to the valuation of s. And now, again, take minus signs into account. This means we obtain a ray that goes diagonally upwards, like that. And case 3, finally, what if the valuation of s is equal to 1? Then it is possible that s starts with minus t plus some higher order terms, right? And then minus s minus t is just, well, the higher order terms, whatever they are. So that means the valuation of s is now going to be 1, respectively minus 1 is minus 1. And the valuation of the second component, which is minus s minus t, is anything bigger. So we obtain a downwards ray looking like this. And now we compare with the other side. On the other side of the equation, so this was the degeneration of the algebraic curve, which we discussed right now. And when I've drawn the rays, I've been maybe a bit quick already, because honestly, you obtain only points in q to the 2, because we're talking about Puiseux series, which have rational exponents. So we obtain only points in q to the 2, but then we take a Euclidean closure. And then this is the picture we obtain for the left-hand side of our equation in Karls theorem. So we do see a piecewise linear graph, which is already exciting. But now we want to compare with the right-hand side to really convince ourselves that we have this equality. So what is trop P for us? It is the max of x, y, and minus 1, because we're taking minus 1 of the coefficients of our polynomial, right? When we do a tropicalization of a polynomial. Okay, and now to figure out the corner locus of trop P, what do we have to do? Well, we have to always set 2 regions of linearity equal and bigger or equal to the other. So x can be equal to y, bigger or equal to minus 1, or x can be equal to minus 1, bigger or equal to y, or y can be equal to minus 1, bigger or equal to x. And you see that gives us precisely the same 3 rays we've just been discussing. Yeah, and so we get precisely the same picture. And so we have an example that confirms that Karls theorem really works. Okay.
Right. Thank you. Yeah, I think this is nice. Maybe you can quickly just give an overview of the valuation.
An overview of the valuation?
I think you've already covered that in the lecture today at the beginning, so probably this is fine. If
you tell me.
Yeah, if you've covered it at the beginning.
Yes, I have.
Yeah, then this is perfectly fine. Thank you.
Okay, good. Good. Then, yeah, I guess I see you all tomorrow, right?
Yeah, that's it.
Okay. Bye-bye. See you tomorrow.
See you. Bye-bye.